The rocky coastline of Ynys Môn in North Wales has a long history with nuclear power. Until 2015, this quiet beach sat in the shadow of Britain's oldest operating nuclear plant. By 2021, the ambitious plan to replace that facility with a massive reactor was completely scrapped. For a country aggressively racing toward net zero emissions, losing that site was a serious blow. The failure came down to what economists call diseconomies of scale. When traditional nuclear plants get larger, they actually become less efficient. They mutate into sprawling civil engineering megaprojects, plagued by decade-long delays and exploding budgets. Managing these bespoke work sites means starting from scratch in a muddy field. You coordinate thousands of workers, navigate a maze of regulations, and build directly in the elements. If we are going to hit our energy targets, building bespoke megaprojects in muddy fields has to be completely abandoned. That realization led to the UK government's recent £2.5 billion partnership to revive the Wylfa site, this time using 3 small modular reactors, or SMRs. Once operational, these 3 units will generate enough baseload electricity to reliably power 3 million homes for the next 60 years. To make this happen, Rolls-Royce is leaving the core physics of the reactor alone. Instead, their engineering focus is entirely on overhauling the manufacturing process. By treating a nuclear plant as a factory-produced commodity rather than a bespoke construction site, engineers can guarantee these critical energy lifelines actually get finished on time. Inside, the Rolls-Royce SMR relies on standard pressurized water reactor technology, utilizing the exact same uranium dioxide fuel that has safely powered global grids for decades. The real engineering achievement is the packaging density. They have managed to compress 470 megawatts of continuous power generation into a fraction of a traditional footprint. Looking at this 3D architectural rendering, you can see how the entire operational plant fits securely beneath a single site canopy. The whole layout covers just 5.3 acres, which is roughly the size of 2 football pitches. Shrinking the site down to this size enables a divide-and-conquer strategy. It allows engineers to pull the most complex, time-consuming construction tasks off the critical path and out of the weather entirely. They achieve this through strict modularity. The entire power station is broken down into about 1,500 standardized, transportable components, everything from heavy pressure vessels to mechanical systems and civil engineering kits. Traditionally, large reactors rely on an EPC model: engineering, procurement, and construction. As this footage of a conventional build shows, all the risk is concentrated in a chaotic, sprawling construction site vulnerable to weather and labor delays. This diagram outlines the replacement for EPC. It highlights the new engineering, manufacturing, and assembly model, or EMA. Under EMA, 90% of the manufacturing and testing is relocated into highly controlled, weatherproof off-site factories. When the finished modules are finally shipped out to the Wylfa site canopy, the workers aren't doing complex fabrication. They are purely focused on lifting, placing, and jointing the pieces together. This site as a factory approach slashes the total build schedule down to a highly predictable 3.5 to 4 years. Relocating the hardest engineering tasks into a controlled factory setting keeps budgets intact, making the process of scaling nuclear power financially viable. Predictable manufacturing also transforms the reactor into a massive employment engine. The Wylfa deployment alone is projected to create 8,000 highly skilled jobs. That breaks down to 3,000 roles directly revitalizing the local Anglesey community, with another 5,000 jobs distributed across the national supply chain. Because the SMR is a standardized, repeatable product, the financial risk plummets. This creates a highly investable asset that easily attracts the private capital needed to build it. Predictable economics and localized job creation turn these deployments from heavy public financial burdens into robust national economic engines. And Wylfa is just the starting point for fleet deployment. Once the supply chain and factory infrastructure are established, those same facilities can endlessly churn out identical reactors for sites across the globe. The future of nuclear power looks less like giant concrete monoliths rising slowly over decades, and much more like a sleek, high-tech assembly line. Securing a domestic, standardized manufacturing pipeline insulates the national grid against volatile global markets and unpredictable supply chain shocks. True energy independence relies on mastering the assembly line that builds the reactors, ensuring a steady, reliable flow of clean power for generations to come.